So here's a sentence that sounds like it's contradicting itself. Rare earth elements aren't actually rare. I know it's not a unique statement nor is it very dramatic, but then we are talking about the periodic table after all. So we are going to discuss why they are not rare on this planet anyway. They're diffuse, spread thin, annoying to mine, chemically clingy to their neighbors, but there's enough of most of them in Earth's crust to embarrass the name. That's a story about geology and refining and, lately, geopolitics. It is not this channel's job today. There's a sister show that already did the economics of that particular headache, and did it better than we would. Here's the question that show wasn't built to ask because it's a policy show, not a physics one. Is anything in the periodic table actually rare? Not economically rare. Not hard to mine rare. Cosmically rare. As in, did the universe make plenty of it or did the universe barely manage to make any at all? Turns out the answer splits the table almost exactly in half, and the dividing line isn't politics. It's iron. Everything up through iron, the universe makes constantly everywhere as a matter of routine stellar housekeeping. Every star doing ordinary business is quietly manufacturing it. But everything heavier than iron, including most of what actually gets called rare earth, and including gold, platinum, and the uranium sitting in your smoke detector, needed something stranger than a star doing its job. It needed something closer to a crime. Humanity confirmed what that crime actually looks like for the first time in 2017. We'll get there. But first, the boring tier, the part of the table the universe hands out for free. Start at the beginning because the beginning is short. The Big Bang itself only ever made 3 elements worth mentioning: hydrogen, helium, and a whisper of lithium. That's it. No carbon, no oxygen, no iron. Nothing you or the chair you're sitting on is actually made of. Big Bang nucleosynthesis had about 20 minutes to work with before the universe expanded and cooled past the point where fusion could continue. Footnote 1. And 20 minutes is enough time to build the 3 lightest elements and not 1 atom more. Everything else, every element that shows up in your body, your phone, your car, got built later inside stars 1 nucleus at a time. Here's the mechanism, stripped of the jargon. Stars are fusion reactors that survive by fighting gravity. Fusing light nuclei into heavier ones releases energy, and that outward pressure is the only thing holding a star up against its own weight. A star spends its life fusing hydrogen into helium, then helium into carbon and oxygen, then, for big enough stars, working its way up the table 1 element at a time, extracting a little less energy at every step. This process runs continuously in every star doing ordinary business, everywhere in the observable universe right now. This is the paper that first laid the whole picture out properly. Burbage, Fowler, and Hoyle 1957, universally just called B²FH by people in the field, and it's one of the genuine great works of 20th century physics. Footnote 2. It's also, not coincidentally, the paper connected to a myth this channel has already had to correct once, Fred Hoyle's carbon prediction, and the retrofitted, he did it for life, story that turned out not to be how his own contemporaries described it at the time. Footnote 3. Worth flagging honestly, Hoyle is a recurring character in this show's sourcing, and he keeps being more careful in the actual historical record than the popular version of him gets credit for. The fusion ladder runs out at iron. Fusing elements lighter than iron releases energy. Fusing elements at or past iron costs energy, the reaction stops paying for itself. A star can build iron. A star cannot, through ordinary fusion, build anything past it. This is the actual physical reason a star's core eventually goes quiet, collapses, and, for big stars, detonates as a supernova. Iron isn't a random stopping point. It's the exact atomic weight where the universe's energy accounting flips from profit to loss. So here's the part where I have to be honest about what rare earth actually means because I got this wrong myself before doing the reading for this one. The elements everyone's arguing about in chip factories and mining contracts right now, the lanthanides mostly, aren't rare, because the universe struggled to make them. Cerium, the most common one, is roughly as abundant in Earth's crust as copper. Footnote 4. They're called rare because they're chemically almost identical to each other, so nature never sorts them into neat, concentrated deposits the way it does with, say, iron ore. It's not a production problem. It's a filing problem. The universe made plenty. It just never bothered to organize its own paperwork. That's the easy tier. Hydrogen through iron, manufactured constantly, everywhere, as a byproduct of stars simply existing. Now for the tier that isn't easy at all. The tier that includes most of the actual lanthanides plus gold plus platinum, plus the uranium that keeps this planet's interior warm enough to have plate tectonics. None of that comes from ordinary stellar fusion. All of it needed something closer to a collision. Past iron, the only way to keep building heavier elements is neutron capture. A nucleus absorbing free neutrons faster than it can decay them away, climbing the periodic table sideways instead of through fusion. Footnote 5. There are two speeds this can happen at. The slow version, the S process, happens gradually inside certain aging stars over thousands of years, and it accounts for a real chunk of the heavy elements in the universe. It is, frankly, a little dull, and this show has no interest in dull. The fast version, the R process, rapid neutron capture, is where things get interesting because it requires an environment so thick with free neutrons that a nucleus can absorb dozens of them before it has time to decay. You cannot get that environment inside a normally functioning star. You need something closer to a wound. For decades, the leading candidate was core collapse supernovae, the theory being that the neutron-dense environment right after a massive star's core collapses might be violent enough, briefly enough, to do the job. Also footnote 5. It was a reasonable guess. It was also, for about 60 years, completely unconfirmed. Nobody had ever actually watched an R process event happen and checked what came out of it. That changed on August 17, 2017. LIGO and Virgo detected a gravitational wave signal, GW170817, lasting about 100 seconds, produced by two neutron stars spiraling into each other and merging. Footnote 6. Neutron stars are already among the densest objects that exist without being a black hole. Slamming two of them together throws an enormous quantity of neutron-rich matter outward fast into space. Within hours, telescopes across the electromagnetic spectrum found the visible counterpart, a kilonova, an optical flash from the merger. And for days afterward, spectroscopic follow-up watched its light change in exactly the way heavy R process elements decaying and cooling would predict. Footnote 7. Strontium was identified in the ejecta directly. This is, as far as anyone can tell, the first time our species watched a chunk of the periodic table get manufactured in real time and checked the receipt. And it is very fascinating. For roughly 100 seconds, two collapsed stars produced a quantity of gold, platinum, and heavy rare earth material that would take an ordinary star billions of years of fusion to even approach, and could not approach at all past iron by fusion alone. The universe did not build this tier of the table patiently. It built it violently, rarely, and almost entirely by accident. This is the crime scene in the literal sense the title's reaching for. Not a metaphorical one, an actual forensic event with a specific date, a specific signal, and a specific chemical fingerprint left in the wreckage. Footnote 7. And here's the thing that makes it matter for everything after this section. Neutron star mergers are not common, and they are not fast to arrive. It takes billions of years, on average, for two neutron stars in a binary system to spiral inward and finally collide. Which means the heaviest, rarest tier of the periodic table wasn't just hard to make. It was slow to start showing up, on any timescale a universe actually has to work with. That's not a footnote. That's the whole next section. Here's where this connects back to something this channel has already argued from a different angle entirely. The temporal lottery made the case that the universe's habitable stretch, the stelliferous era, the period when stars are actively forming and shining, is itself a finite window bounded on both ends, and that existing anywhere inside it is itself a piece of evidence about when you're allowed to be asking these questions at all. That episode was mostly about time in general. This one is about something narrower and, honestly, stranger. A second window nested inside the first one, defined not by whether stars exist, but by whether enough of the slow, violent tier of the periodic table has had time to accumulate nearby. Life, as far as we can build it out of known chemistry, doesn't just need carbon and oxygen, the easy tier manufactured everywhere, constantly, since the first generation of stars. It also needs, in smaller quantities but non-negotiably, elements from the hard tier. Phosphorus for the molecular backbone of DNA, iodine for basic biochemistry, molybdenum as a metabolic catalyst, and, less obviously but arguably more importantly, radiogenic elements like uranium and thorium, whose slow decay inside a planet's interior is a major source of the internal heat that keeps something like plate tectonics running at all. None of that tier existed anywhere in the early universe. The first generation of stars, population 3 metal-free, built from nothing but the Big Bang's hydrogen and helium, couldn't have produced it, because it hadn't been produced yet anywhere for them to inherit. Each subsequent generation of stars enriches the interstellar medium a little further, and the rare, violent R-process events, the mergers, accumulate their contribution on a much slower, patchier timeline than ordinary stellar fusion does. There's even a genuine puzzle here worth naming rather than smoothing over. Some of the oldest, most metal-poor stars we can observe, in particular a cluster of them in the dwarf galaxy Reticulum II, show R-process enrichment that looks too early and too concentrated to easily explain if neutron star mergers, with their billion-year-plus in spiral times, were the only source running that far back. Something produced that material fast, early and locally. Whether that's a rarer, faster class of merger event, some subset of unusually magnetized supernovae, or a mechanism nobody's confirmed yet is a real, live disagreement, not a solved footnote. More on exactly how live in a moment. Because I have been asked to explain why a universe would need to wait before it could build something capable of asking why it had to wait. I do not find the delay itself confusing. 'Cause requires time. That part is simple arithmetic. What I find myself returning to is smaller. Somewhere between no heavy elements exist yet, and here is a planet with plate tectonics, radioactive heat, and a stable surface. A specific quantity of cosmic time had to elapse, and elapse in a fairly narrow band, near this particular patch of a particular galaxy. I am attempting to hold that as a fact rather than a coincidence. I'm not certain I am succeeding. There's a floor, then, on how early a chemistry like ours could ever have existed, set not by when stars turned on, but by when enough mergers had already happened nearby to leave their fingerprints in the local supply of raw material. And there's a ceiling too, further out, deep enough into the universe's future, star formation itself tapers off, fresh fuel runs out, and the merger events that build the heavy tier become steadily rarer, then effectively stop. The window for building a chemistry that needs both tiers of the table, the easy one and the crime scene one, isn't the same as the window for stars existing at all. It's narrower on both ends than that. Worth being precise here about which parts of this argument rest on confirmed measurement and which parts are still being argued out in the literature, because they are not the same tier of confidence, and the show shouldn't present them as if they were. Solid, essentially uncontested, Big Bang nucleosynthesis producing hydrogen, helium and trace lithium and nothing heavier. Footnote 1, ordinary stellar fusion building the table up through iron, and the energy cost cliff at iron being the reason fusion stops there. Footnote 2, and the GW170817 detection itself, the gravitational wave signal, the electromagnetic counterpart, and the spectroscopic identification of strontium in the kilonova ejecta. Footnotes 6 and 7, that last one in particular is about as close to "we watched it happen and checked" as astrophysics gets. Genuinely open and worth naming specifically rather than folding into a vague "scientists are still figuring it out." How much of the total galactic supply of R-process elements comes from neutron star mergers versus some rarer channel of core collapse supernova, the specific class sometimes called magnetorotational supernovae, which some models suggest could produce R-process material faster and earlier than mergers can, though direct observational confirmation of that channel doing so remains thin. Footnote 5. And directly tied to that, the early enrichment puzzle from Reticulum II, old, metal-poor stars showing R-process signatures earlier and more concentrated than a merger-dominated picture comfortably explains, which is precisely the kind of tension that either gets resolved by finding a faster production channel, or forces a real revision of how quickly the early universe could build this tier of the table at all. Neither side of that argument is settled. Both are active research, with named competing explanations rather than a single consensus answer. The distinction matters for the argument in Section 3 too. The existence of a merger-driven crime scene is not in dispute. The exact shape and timing of the resulting cosmic accumulation curve, how early, how fast, how evenly distributed the heavy tier became, genuinely is. The window this episode's been describing is real. Its precise edges are still being drawn. Here's the honest way to put together everything above. The temporal lottery argued that existing at all, in a universe with a finite stelliferous window, is itself a fact worth treating as evidence. That "we are the measuring instrument" applies to when we're standing, not just where. This episode has been quietly running a second, narrower version of that same argument the whole time, and it's worth saying it out loud instead of leaving it implied. It's not enough that the universe had gotten around to making stars by the time anything like us could exist. It also had to have gotten around to making enough of the slow tier, the crime scene tier, the stuff that only comes from collisions billions of years in the making, locally, nearby, in the specific patch of galaxy that would eventually become the raw material for a rocky planet with a hot interior and the right trace chemistry. That's not a coincidence layered on top of the first lottery ticket. It's a second lottery ticket, drawn from a much smaller, much slower pool, that also had to come up favorable before any of the rest of this was possible. We are not just downstream of stars existing. We are downstream of a specific rare violent event having already happened enough times, close enough by early enough, but not too early, for its wreckage to end up in the dust that became this planet. That's a stranger thing to be the product of than a star existed nearby. It's closer to being the product of an accident that had to happen more than once, in roughly the right neighborhood, on roughly the right schedule. There's still a lot of universe left to look at. Most of what you're made of came from something as unglamorous as stars doing their job quietly for billions of years. But a small, disproportionately important fraction of you, the part of your biochemistry running on phosphorus and iodine and molybdenum, the part of this planet still warm inside because of uranium that's been quietly decaying since before there was a planet to warm, that part came from 100 seconds of two dead stars colliding, somewhere, a long time before the sun existed to catch any of it. That's not a violent origin story you're meant to find alarming. It's just the actual one. It's a Tuesday. Some of what's holding you together is stardust, same as always, and a smaller, stranger piece of it is aftermath. There's still a lot of universe left to look at,